Hi everyone, this is Stephen Pu. I'm the founder of Taraxa, and today I will talk about the true finality inside the Taraxa network. Before we talk about true finality, let's talk about why it's necessary, right? And we get to this sort of idea of reordering or reorganization risk inside a blockchain network. Um, as we talked about before, right, we talked about this mechanism by which we actually order blocks inside our block DAG. And as you can see, the ordering of these blocks is an evolving process, right? So as more blocks, newer blocks are added into the DAG's frontier, the order or the anchor chain, the weights and all these other things, they're evolving, they're constantly changing. So the ordering of these blocks do get changed over time, right? Now, what we actually do observe is that there is a very steep fall off in the risk of any specific block getting reordered as a function of time, right? So this, as time goes on, this is sort of probability of a reorder, right? So there's a steep fall off. However, the risk of reordering never really goes to zero, right? Never really goes to zero. And also, something like this here, where maybe the risk falls to like 1%, is actually takes quite a while, right? So what we actually want to happen is we want to just say, hey, at around this time, we just want the risk to go to zero, like absolute zero. There's no risk of anything getting reordered, right? So what's so bad about reordering? Well, in our specific use case, for example, the which actually is audit logging of informal agreements or informal transactional data generated by people or machines, right? The order in which events occur is actually pretty important, right? So because if you get into a lawsuit, for example, over some disagreements or disputes, who said what when is actually very, very important. And the when part is often very critical. Did you talk to me before you talk to this other stakeholder, for example, right? So we want to make sure that order is preserved and that people are confident, our users have this confidence that when something is anchored into the blockchain, that it is truly immutable, right? And there's no risk of reordering. And they get that confirmation almost right away. Right? So that's why we want to introduce what we call true finality into the block DAG. So how do we do that, right? So what we do is that at the top here, we have this portion, right? This is the block DAG right here, right? As we talked about before, this part. And in parallel, we have this very fast PVFD process, right? So what this process does is that it would just periodically, asynchronously with the block DAG, it would just say, hey, right now we're gonna vote on which block to finalize. To add infinite weight, right? Infinite weighting. So this time we're gonna add infinite weight to this block. Boom. So this block is now finalized. And next time we're gonna add infinite weight to this block, right? And when we have two blocks with infinite weight, all the blocks that belong to epochs between them along the anchor chain, the ordering of those blocks are also completely finalized. Okay, so what we essentially actually done is that we finalize an entire period, right? We call this a period of a block. You can think of this as sort of like a unit of progression, right, inside the blockchain, inside our block DAG, is that this portion of the blockchain has now become absolutely immutable with no risk of reordering, no risk of anything, right? It's just not going to change ever, right? And this PVFD process runs in parallel, in asynchronously with the rest of the block DAG, and it just keeps on finalizing these period blocks to make sure that there is absolutely zero risk of reordering for the ones that it has finalized. The PVFD process is actually pretty simple. It's a well-known process. Basically, for us, the way we implemented it is that first, there's a proposal process, right? Somebody proposes it, and then there is a selection of who is the person that is going to win, right? Who is the person that's going to win this specific round, and he gets to be the guy and we're all going to look at the block that he proposes to finalize, right? And this is done through a random VRF process. And once we selected the person who gets to speak, I think in this process it's called a leader, then we look at, okay, so which block is the block that he or she is proposing, that is going to be finalized. The reason we pick the winner first or the leader first before the block is because the message that contains the winner or the leader eligibility is a much smaller packet, so it actually travels through the network probably much faster than the actual block message. So then we vote on the period, which the period block, and then we vote whether or not everyone says it's done, right? So have we reached over 3/4 of the votes? I've seen over 3/4 of the votes, but then everyone else in the committee see 3/4 of the votes, right? And we counted that, then it's time to propose the next one. So this process just keeps on going over and over and over again. The reason why this is a highly scalable process is because the number of people that actually ever get involved in this is a randomized subcommittee of the entire block proposing pool, right? So while the entire block proposing pool gets involved, obviously, also through random selection through the through the combination of a randomized lay determined by BRVDF inside the block DAG. Everyone also locally calculates in parallel whether or not they are eligible to actually participate in the block finalization process, right? If they are eligible, they submit the proof of their eligibility. Everyone sees who has, for example, the lowest number. Then that person's block proposal for finalization comes under vote. Everyone agrees. People think that they've seen the majority. They say, I've seen the majority. Everyone else seen the majority. Can we move forward? We move forward. It starts over again. So every single time is only a very small subset of the entire network that actually gets participating in this, and that subset is randomly selected. So it's both fair as well as scalable, right? So this is how we introduce true finality into Taraxa's block DAG. Thank you.